Okay, students, let's start with the lecture today on elementary probability theory. Okay, I hope I'm audible to everyone who is attending the lecture today. This is a fresh unit in statistics, and it holds a lot of importance as well as weightage in the exam as well. Okay. Your readings for stats, as I have mentioned to everyone, it's JL Devore. Okay, but you just have to do the lecture notes. The lecture notes are sufficient. They contain all theory, all proofs, everything. So let's quickly start. So we have done probability multiple times before. We have done it in class 11, 12th. We have done it in at initial levels as well. So all of us should be familiar with some terms before we go into the depth of probability. So the first term you can see on your screens, this is called as sample space. Okay. So all of us should be familiar with what is an experiment. So an experiment is any activity or process whose outcome is subject to uncertainty. Okay. When we talk about an experiment, we don't exactly know the outcome of the experiment. Okay. All what we can say is that we can expect one outcome with some probability, another outcome with some probability. So an experiment is an activity whose outcome is uncertain. Sample space, all of us know what is meant by sample space of an experiment. Sample space of an experiment, which we denote by delta, is the set of all possible outcomes of that experiment. Okay, so when we talk about sample space, it will consist of all possible outcomes of that particular experiment. For example, you can see on your screens, suppose we conduct an experiment of examining whether a single fuse is defective. Suppose you want to see whether a single fuse is defective or not. So my sample space delta will be the set of two outcomes, either defective, which stands for D, or not defective, which stands for N. So my sample space will be the set of N comma D. Okay, suppose I have 3 fuses and I need to check whether the fuse is defective or not. What are the options I have? All of you can see on your screens. One possibility is all the three fuses are not defective, N and N. Second possibility is that first two are not defective, but the third one is defective. And similarly, so I can come to the white screen to explain it. Okay. Suppose there are three fuses being selected, and I need to check how many of them are defective and how many of them are not defective. So if I'm selecting three fuses, what are the possibilities I have? Either all of them will not be defective, or all of them will be defective, or I'll have a possibility of first two not defective, third one defective, or a possibility of not defective, defective and non-defective, or I'll have a possibility of D and N, okay, or I'll have a possibility of D and D, or I'll have a possibility of DDN, or I'll have a possibility of NDD, okay. So you can see there are how many possibilities? All of you can see the number of possibilities on your screens. There are 8 possibilities, okay. In general, you see, you must have done this in school also, that in general, how many outcomes we have when we have two options, how many outcomes we have? 2 to the power n. So in this particular case, we have 3 fuses. So if we conduct an experiment, the sample space will consist of how many elements? The sample space will consist of 2 to the power n elements. So delta, which is the sample space, will consist of how many outcomes? 2 to the power n outcomes. In this particular case, what was my n? My n was 3 fuses. So 2 cube, which is 8. I hope all students are clear with this. Okay, so till now, what have we done? I'm quickly revising. We have done what is meant by an experiment, any activity or process whose outcome is subject to uncertainty. What is meant by sample space? Sample space of an experiment includes the set of all possible outcomes of that experiment. Suppose we want to see whether a single fuse is defective or not, sample space will just be either you'll pick up a defective fuse or you'll pick up a non-defective fuse. Suppose you consider an experiment of picking up 3 fuses in sequence to see whether they are defective or not. Answer will be 2 to the power 3, which is 8. Okay. Suppose you pick up 2 fuses. Let's take up that case also. Suppose I take up 2 fuses. Suppose my n was 2 fuses. And we need to check whether they are defective or not defective. Then in that particular case, my sample space will be NN, DD, DN and ND. This will be my sample space. It will consist of how many outcomes? It will consist of 2 to the power n, which is 2 to the power 2, which is 4 outcomes. Okay, then let's continue. Okay, now what is meant by an event? So that is the next topic for us. So an event is any subset of the outcome in the sample space delta. All of us know what a sample space now is. Set of all possible outcomes of the experiment. When we take a subset of it, it is called an event. Okay. All of us know what a subset is, right? All of us have done set theory, so we know what a subset is. Okay. An event is said to be a simple event if it consists of exactly one outcome, and compound event if it consists of more than one outcome. Okay. You can read the note in general, exactly one simple event will occur, but many compound events will occur simultaneously. Now, to understand this particular note, let us look at the example. Consider an experiment in which each of the three vehicles taking a particular freeway exit turn left or right. Okay. The sample space is given to us. You can see it. Now, what are the possibilities we have? There are three vehicles and they can turn either left or right. So what are the particular possibilities we have if we want to list them? You can see on your screens. Again, you can see that there are three possibilities. Okay. So I can come to the whiteboard to explain. Suppose there are three vehicles and they can turn either left or right when taking a freeway exit. Okay. So what's the sample space? Sample space will be either all three can turn left, or first two can turn left, third one can take right, or left right left, or right left left, or right left right, or right right left, or left right right, and the last option would be right right right. This is my sample space. Now consider the following events. Consider the following events. Suppose A is the event exactly one of the three vehicles turn right. Exactly one of the three vehicles turn right. So what will my answer be? If exactly one of the three vehicles turn right, it means I'll take up this LLR because exactly the third vehicle turns right. Similarly, I'll take LRL and I'll take LLR or RLL. Okay, so exactly one of the three vehicles turned right. This is my answer. Similarly, if I tell you at most one of the vehicles turned right, suppose B is the event, at most one of the vehicles turn right. What will the answer for this be? At most one of the vehicles turn right. It means there are two options, either none of them turn right, it means all of them turn left, or exactly one turns right, which means we have already found out LLR, LRL, RLL. So these are all examples of compound events because they consist of more than one outcome. You can see A also consists of more than one outcome. It consists of three outcomes, and B also consists of four outcomes. That means they are all examples of compound events. Okay, now to understand the note, suppose this experiment was actually conducted to see whether the vehicles take left or right on the freeway exit. Suppose the experiment was actually conducted, and suppose the outcome came out to be LLL. Suppose the outcome came out to be LLL. Suppose when the experiment got actually conducted, all three vehicles took the left exit. Now you can see this is a single event. If you can see, this is what This is a simple event. Why is it a simple event? Because it consists of exactly one outcome. But you can see multiple outcomes, multiple events are occurring simultaneously. Why? Because LLL is occurring here also. At most one of the vehicles turn right. Okay, so when a simple event occurs, compound events also occur simultaneously. When I say that all the three vehicles have turned left, that's a simple event. But then that event is also a part of B. At most one of the vehicle turns right. Now at most one of the vehicles turned right also includes LLL. So what we learn from this is, I am writing it on the screen. What do we learn? In general, exactly one simple event, in general, exactly one simple event will occur, but many compound events occur simultaneously. But many compound events occur simultaneously. It means at one particular point of time, only one simple event will occur. But many compound events will occur simultaneously along with it. I hope this is clear to everyone. Anyone who has any doubts can ask. This is solved in the lecture note also. You can see this. It's exactly the same what I've discussed on the whiteboard. Till here, anyone has any doubts? I'm open for doubts. Before we move forward, anyone has any doubts can ask. Okay, then the next thing, relations from set theory. So we are now combining set theory with probability. Okay, so let's look at the following terms. What is meant by complement? So all these terms we have done in set theory also. We are revising them and we are now adding probability to it. So when I talk about complement, the complement of an event A denoted by A complement is the set of all outcomes in the sample space that are not contained in A. Set of all outcomes in the sample space that are not contained in A. Union, all of us know, the union of two events A and B denoted by A union B is the event consisting of all those outcomes that are either in A or in B or in both the events. So when I talk about A union B means outcomes either in A or in B or in both. Another way of talking about union is all outcomes in at least one of the events. So whenever in the question you see at least one means union only. They are asking you union only. Okay. Then what is meant by intersection? So the intersection of two events A and B denoted by A intersection B is the event consisting of all outcomes that are in both A and B. Set of outcomes that are in both A and B. So when I talk about union, it means or. When I talk about intersection, it means and. So I hope all of you are comfortable with the three operations. A complement means set of all those outcomes in the sample space which are not contained in the set A. Union means set of outcomes either in A or in B or in both. Another name for union, at least one. At least one of the events means union only. Intersection When I talk about A intersection B, set of outcomes that are in particularly in both A and B. Okay. You can see the following example. We are given the sets A, B, and C. You can see on your screens. A is 0, 1, 2, 3, 4. The sample space is 0, 1, 2, 3, 4, 5, 6. B is 3, 4, 5, 6, and C is set of 1, 3, and 5. Now, if I have to find A complement, what will I do? From the sample space, I will remove A. If I remove A from the sample space, I get 5 and 6. That is my A complement. Okay. What will A union B be? A union B will be, you just add all elements in A and all elements in B. So that will be 0, 1, 2, 3, 4, 5, and 6. And you can observe A union B is nothing but the sample space delta itself. If I have to find A union C, again add elements of A and C together in one particular set. So 0, 1, 2, 3, 4, and 5. A intersection B is the common elements of A and B. So if you look at A and B, what are the common elements? The only common elements of A and B are 3 and 4. So A intersection B is 3, 4. Common elements between A and C are only 1 and 3. So A intersection C is set of 1, 3. And A intersection C complement. A intersection C complement means first you'll find A intersection C. A intersection C is 1, 3, set of 1, 3. You will remove that from the sample space. So if I remove set of 1, 3 from the sample space, what do I get? 0, 2, 4, 5, and 6. So A intersection C is set of 1, 3. Once I remove this from the sample space, A intersection C complement is 0, 2, 4, 5, and 6. I hope no one has any doubt with this example. It's a very basic example. You've done this even in class 11th also. So, okay. What is meant by mutually exclusive and mutually exhaustive events? So that's the next definition for us. So first of all, let's come to mutually exclusive events. So when are events said to be mutually exclusive? If they have nothing in common. That means their intersection is a null set. How do we denote the null set? Remember, we use the donation phi. So let phi denote the null event. That is the event consisting of no outcomes. When the intersection between A and B is exactly equal to phi, we say that A and B are mutually exclusive, and a synonym for mutually exclusive, disjoint events. A and B are disjoint. Disjoint means they have nothing in common. Okay, so coming to the whiteboard, we can draw Venn diagrams for all of these. We have done this in maths also before. Just a quick revision. So if I draw Venn diagrams, the first thing we need to draw, okay, if I have to draw A union B, this is my entire sample space. This is set A, this is set B. A union B is the set of outcomes in A or B or both. That means the whole shaded area is A union B. If I have to draw the diagram for A intersection B, the set of outcomes which are particularly in A and B both. So this is A, this is B, set P, and A intersection B would be this shaded area, because these are the set of outcomes which are in both A and B. Remember, we write A union B as A or B. we write A intersection B as A and B. So intersection means and, union means or. Okay. Third thing, we need to find what is A complement. So A complement is nothing but all the area outside A. This is my A. So A complement will be everything outside A. It means those outcomes which are not contained in A. That is A complement. And if I talk about, suppose A and B are mutually exclusive. Suppose A and B are mutually exclusive events. Mutually exclusive events means they have nothing in common. So this is my sample space delta. And you can see A and B are not intersecting. Why are they not intersecting? Because they have nothing in common. It means the intersection of A and B is exactly equal to the null set phi. Okay, this is meant by mutually exclusive events. When are events said to be mutually exhaustive? Okay, events are said to be mutually exhaustive. This is just an extra information for you. Events are said to be mutually exhaustive. They are said to be mutually exhaustive if they cover the entire sample space. Entire sample space. So I will say that A and B are mutually exhaustive. A and B are mutually exhaustive if the union of A and B is exactly equal to the universal set. If the union of A and B gives me back the universal set delta, it means the events A and B will be mutually exhaustive. Okay. I hope all of you are clear till here. Open for doubts if any. You can see the definition of mutually exclusive on your screens. You can see the Venn diagrams. We have drawn the Venn diagrams. Okay. Now the next thing, axioms, interpretations, and properties of probability. So let us look at these axioms. Now what does probability do? Probability assigns to every event A, the probability assigns a number P of A, which will give a precise measure of the chance that the event A will occur. So probability is mapping what? Probability is mapping all the events to values between 0 and 1. What is probability actually doing? It is mapping the, so if I talk about probability, my domain is the set of all events. Domain is the set of all events. What is my codomain? My codomain is the values between 0 and 1, including 0 and 1. And probability is a function which maps the set of all events to the values between 0 and 1. I am using mathematical touch here to explain you. Probability is a function which maps the set of all events in the domain to values between 0 and 1 in the codomain. It's a function. Okay. Then let's look at the axioms of probability. Axiom 1, for any event A, probability of A is greater than or equal to 0. Obviously, you can't have a negative chance of an event occurring. Either the chance of an event occurring is 0 or it's positive. Okay. Axiom 2, what is the probability of delta? What was delta? Delta is the sample space. Now, no matter which event occurs, sample space will always occur. So probability of delta is exactly equal to 1. Probability of delta is exactly equal to 1 because no matter which event occurs, the sample space is always occurring. Because any event is always a part of the sample space. So probability of the sample space occurring is exactly 1. Okay. Axiom 3. If A1, A2, A3 dot is an infinite collection of disjoint events, then probability of A1 union A2 union A3 union dot is summation as I goes on from 1 to infinity probability of AI. Okay, that means suppose A1 to A1, A2 to A3 is an infinite collection of disjoint events. Disjoint events means they have nothing in common. Their intersection is phi. Then probability of A1 union A2 union A3 union so on will be the summation as I goes on from 1 to infinity probability of AI. So I can come to the white screen to explain the last axiom to you. Okay, so this was axiom 3. I am again explaining it on the whiteboard. Suppose we have A1, A2, A3. Suppose all of these are an infinite collection. Suppose they are an infinite collection of disjoint events. Disjoint events means they have nothing in common. Then if I have to find probability of A1 union A2 union A3 dot, this will be probability of A1 plus probability of A2 plus probability of A3 plus it will continue. Okay, and this how can I write it? I can write it as summation as I goes on from 1 to infinity probability of AI. This will be nothing but summation as I goes on from 1 to infinity probability of AI. Okay, an important proposition for us to understand. So I'm doing the proposition on the screen first. Probability of phi is what? Probability of phi is always equal to 0. What does this mean? This means probability of a null event happening is exactly equal to 0. So what we can do is we can try and we can prove this. So if I let's prove this. Okay, suppose consider the infinite collection. Consider the infinite collection. We are using axiom 3 to prove this. Consider the infinite collection. Suppose A1 is phi, A2 is also phi. Suppose all these are phi events, A3 is also phi, and so on. Now, all of us know, we know that phi union phi is equal to phi, and phi intersection phi is also equal to phi. That means if I use this formula, suppose I use this formula here, probability of what is A1, A2, A3, A1, A2, A3, all these are phi. So सभी phi's का union क्या होगा? सभी phi's का union phi होगा, is equal to, look at the term I am circling, summation as I goes from 1 to infinity probability of AI. अब one particular AI is exactly equal to phi. So I ask you guys, how can P of phi be equal to its sum? How can P of phi be equal to its sum? A number can be equal to its sum only when the number is exactly equal to 0. A number can be equal to its sum when the number itself is equal to 0. So I am again repeating the proof with you. We had done axiom 3. Axiom 3 ये कहती है कि अगर A1, A2, A3 डॉट डॉट और अगर ये सारे डिसजॉइंट इवेंट्स हैं तो प्रोबेबिलिटी ऑफ A1 यूनियन A2 यूनियन A3 and so on till infinity will be equal to P of A1 plus P of A2 plus P of A3 dot 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 continued, which I can write summation as I goes on from 1 to infinity P of AI. Now इस axiom 3 को use कर करके we are proving the proposition that P of phi is equal to 0. That means probability of a null set is equal to 0. इसको हम प्रूव कैसे करेंगे? सपोज हम A1, A2, A3 डॉट डॉट डॉट, सपोज हम सबको phi ले लेते हैं, तो A1 is also phi, A2 is also phi, A3 is also phi and so on. अब हम सबको पता है कि phi union phi is equal to phi and phi intersection phi is also equal to phi. तो अगर मैं axiom 3 यूज करूं तो प्रोबेबिलिटी ऑफ A1 यूनियन A2 यूनियन A3, अब A1 भी phi है, A2 भी phi है, A3 भी phi है, सभी phi's का यूनियन क्या होगा? Phi should be equal to summation as I goes on from 1 to infinity P of AI. Summation as I goes on from 1 to infinity P of AI. अब AI अपने आप में क्या है? AI अपने आप में भी phi है, because सारे A's phi हैं. Now the question which comes is, when can the number be equal to its sum? A number P of phi will be equal to its sum only when the number itself is equal to 0. So hence proof. Any student who has not understood this proof can ask me. I'm open for doubts. In case you have not understood the proof, you can ask me. I hope this is clear to everyone. Okay, let's come back to the lecture note then. So guys, this is the proof in the solved in the lecture note also. I have solved the proof in the white screen also. Okay, anyone who wants the white screen, I can send it to you, but anyways the lecture notes will be mailed to you. Okay. So the next thing, look at the example. Okay, there was one small thing left in the proof. Suppose a, so the next thing we want to prove, look at this. Suppose A1 to AK are disjoint events, and in addition to these, consider the infinite collection AK plus 1, AK plus 2, all of them are equal to phi. इसका मतलब सपोज A1 to AK disjoint events हैं जो phi के इक्वल नहीं है, लेकिन AK plus 1, AK plus 2 बाकी सारे phi हैं. तो अगर हम लास्ट वाला एक्सियम यूज करें, probability of union as I goes on from 1 to k ai will be probability of union as I goes on from 1 to infinity ai, which is I can write summation as I goes on from 1 to infinity probability of ai. अब 1 to infinity में से सिर्फ 1 to k है जो एक्चुअली नंबर्स हैं, k के बाद तो सारे ही 5 हैं, तो I can write summation as I goes on from 1 to infinity probability of ai as summation as I goes on from 1 to k probability of ai. So यहाँ पे हमने थर्ड एक्सियम फिर से यूज करी है. Okay, so I think this is where I should stop. Any doubts to anyone you can ask. Anyone who is unclear with the proof has a doubt can ask me. You can unmute your mic and ask. Anyone who has any doubts can ask before we close the meeting. I hope it was clear to everyone. Okay, so this is where I stop. The lecture notes will be mailed to everyone soon, as and when you register for the classes. Okay. Okay, guys, this is where I